Welcome to this explainer. Today, we're tearing down the architecture of a deceptively simple feature that hides an absolute masterclass in distributed systems. Open any large-scale consumer app right now and just tap the search bar. What happens? Before you even type a single letter, your past queries drop down. Now, to a user, it looks like a trivial UI checkbox. But today, we're actually looking under the hood of recent searches to see exactly how to derive a durable, production-grade architecture from some seriously strict constraints. Get this, 30% of all searches originate from the recent searches list. That literally means the user never even types a query, they just tap a stored one. Combine that with the fact that half of all users hit the search bar within 5 seconds of opening an app, and suddenly you realize, wow, this isn't just a minor convenience, it's the front door to the entire product. So what does this actually mean for us? It means this tiny little feature is actually a high-stakes distributed systems problem with a brutal 50-millisecond latency budget. Think about it. A third of your search traffic is served before typing. If that list is slow, if it's stale, or worse, if it's missing, you are silently destroying revenue at the very top of your user funnel. The list has got to appear before the user finishes blinking. To build this system layer by layer, here is our roadmap. First, the 4 design axes. Second, bounded versus unbounded data. Third, sync, async, and queues. Fourth, storage tiers and pre-warming. And finally, the inevitable failures. All right, kicking things off with section 1, the 4 design axes, or really, the foundational math. We can't just start drawing boxes on a whiteboard without defining our constraints mathematically. First, our data shape. It's bounded per user. We're only showing about 10 items, right? But it's completely unbounded globally with billions of writes. Then, the access pattern is heavily skewed toward reads on a tiny slice of data. Latency is incredibly tight. That P99 latency must be under 50 milliseconds. And finally, tolerance. A user's recent list can be a few milliseconds stale across devices, sure, but it absolutely cannot be missing. Moving right along to section 2, bounded hot versus unbounded cold. This is our first major decision. This brings us to a huge architectural crossroad. How exactly do we store data that's bounded for the individual user, but unbounded for the overall system? Think about a busy kitchen. The durable pantry holds absolutely everything. That's your unbounded data. But during the dinner rush, only the 10 bounded ingredients you immediately need sit right there on the fast, accessible counter. If you treat all data as unbounded, you're over-engineering for read scale. But if you only build for bounded data, you're going to lose history on cache eviction. We need both. And this leads us right into the classic compute versus storage debate. Pre-computing that top 10 list moves the processing cost entirely from our latency-sensitive read path over to our latency-tolerant write path. If we try to compute on the fly, it's like we're cooking from raw ingredients every single time a user taps the search bar. We blow right past our 50-millisecond deadline. By pre-computing a derived view that gets updated on every single write, our read becomes a lightning-fast, single-key lookup. Reheating meal prep takes no time at all. Now, let's talk about the actual table schema for our durable pantry, which will be a partitioned, NoSQL store like MongoDB. We explicitly choose an append-only event-style structure, so one record containing the user ID, query string, and timestamp. Why do it this way? Because the alternative, embedding an array of queries inside a single user document, creates massive write hotspots and lock contention. Your durable store has to optimize for write integrity and analytics, not for the read shapes. Okay, section 3, sync, async, and queues. It's all about the order of operations. The flow of operations totally dictates the user experience. It's literally like checking into a hotel. You get your room key immediately. That's our synchronous call to Redis, while the heavy backend analytics process in the background asynchronously through Kafka. Step 1, run the search. Step 2, synchronously update the Redis hot store so the UI doesn't look broken if the user instantly switches tabs. Step 3, asynchronously push to Kafka for the durable history log. Look, tying user-facing latency directly to a heavy write database is just engineering malpractice. Now for the mechanics of that fast counter. You might be tempted to just use a Redis list. Honestly, bad idea. A naive list stores duplicates if you search for, say, Golang concurrency twice. Terrible UX. Instead, we use a Redis Z-set or a sorted set, using the Unix timestamp as the score. The algorithm natively deduplicates and atomically bumps the latest query right to the top. This one data structure choice effectively turns 3 separate database calls into just one. Let's look at the actual queries. We use strictly idempotent commands.
A z-add command for writes just updates the timestamp score in place. Done. For reads, a z-reave-arrange command grabs the top 10 newest items in a single, highly efficient logarithmic operation. Because these operations are idempotent, our production-grade Go code can safely retry failed messages from a dead letter queue without accidentally corrupting the user's UI with a bunch of duplicate queries. So what's the actual storage math look like here? For 100 million active users times 10 queries at roughly 50 bytes per query string, that equals just 50 gigabytes. That easily fits in a sharded Redis cluster. Engineers constantly over-provision because they calculate based on total registered users rather than active users. But 50 gigabytes is incredibly manageable for a modern hot-tier caching layer. Next up, Section 4, Storage Tiers and Pre-warming, where we talk about real cost savings.
Look, retaining billions of searches indefinitely in a warm database like MongoDB is incredibly expensive. We have to optimize by tiering. We keep the fast, hot 10 items in Redis. We keep a 6-month durable history in MongoDB for operational queries and support. And then, by pushing the long-tail historical data into S3 via nightly Spark ETL jobs, we completely slash our NoSQL storage costs while still keeping all our analytics capabilities intact. But how do we avoid the dreaded cache miss? We predict and pre-warm the Redis cluster exclusively for daily active users. Think about it. If you have 1 billion registered users, but only 100 million are daily active, relying purely on a cache-on-miss strategy means millions of users are going to experience degraded latency every single morning. Instead, we use login events to preemptively fetch their history from MongoDB and hydrate Redis on the spot. Boom, you instantly get cross-device consistency for free. Which brings us to Section 5, inevitable failures, and those operational blind spots everyone ignores. Because, let's face it, things are going to break. A principal engineer designs explicitly for failure modes. We have to build mitigations for operational fires from day one. If a celebrity account hammers a single Redis shard, we need hotkey detection and replication ready to go. If users invoke their right to be forgotten under GDPR, our pipeline must seamlessly purge that user's history from MongoDB, from cold S3 storage, and from Redis. Retrofitting privacy into an architecture takes months. Designing it upfront is just good engineering. This all forms our observability spine. We monitor that 50 millisecond P99 latency obsessively. If Redis drops offline completely, a circuit breaker flips. Sure, we might return an empty recent list, but the core search bar itself still functions safely. The system degrades gracefully. We're also constantly watching consumer lag on our Kafka streams just to ensure our dead letter queues and analytics aren't falling silently behind in the background. Now, you might be asking yourself, what else can we do with this event stream? Well, by fanning out via Kafka to Elasticsearch, we've actually created an analytics side channel. This powers trending queries, typo mining, and A/B testing, all without impacting user latency whatsoever. Elasticsearch becomes our analytics workbench, while Mongo remains the system of record. Because we publish the initial search event asynchronously, we can spin up entirely new product features based on search behavior without ever touching the critical path. I want to leave you with this final thought. If you master the discipline of deriving an architecture from its strict constraints, you can solve literally any distributed systems problem in this industry. The specific technologies we discussed today, they'll probably be obsolete in 5 years. But this foundational method of deriving architecture, that is a durable skill. So take a hard look at the systems you're maintaining right now. Are you truly building for the user's constraints, or are you just stacking databases? Thanks for joining me on this explainer, and I'll catch you in the next one.